What else can we say about the number of gas molecules which are sitting up here? It would seem to me that if they are up here as a consequence of being able to break free of the surface, there must be some sort of forces that were making them stick here in the first place. So what is the force that made that molecule stick to that molecule, or this molecule stick to this one, or this one stick to this one? At this point, you know what that force is. These are the intermolecular forces that we talked about in detail back in the first semester of the course. So right away, we're borrowing from something we learned back in the first semester, the idea that vapor pressure here must somehow be related to the intermolecular forces. And it doesn't take a brilliant thinker to appreciate that there must be a relationship based upon just how strong those intermolecular forces are. And so we would say then that the stronger the intermolecular forces, the smaller the vapor pressure. In other words, there's an inverse relationship with respect to vapor pressure and intermolecular forces. So, if we're going to be talking about intermolecular forces, then we need to recall what all the different types are. And I'm not going to do a thorough review of intermolecular forces, but I'll point out that when we were doing intermolecular force assignments, one of the things I taught you to do was to create the bins associated with the fundamentally different kinds of intermolecular forces that we had to deal with. And there were 4 of them. There were the instantaneous dipoles, there were the dipole-dipole interactions, there were the hydrogen bonding interactions, and there were ionic interactions. And they varied substantially in terms of their intermolecular forces, from less than a kilojoule per mole for instantaneous dipoles that you saw in symmetrical molecules, to 5 kilojoules per mole or so for dipole-dipole, up to 20 kilojoules per mole for water, and so on. Now, it's also important to appreciate that the number of intermolecular forces sitting inside a molecule mattered. So that if I look at something like an instantaneous dipole for a hydrocarbon, hydrocarbons can actually start becoming liquids fairly quickly, because even though their number of instantaneous dipoles on a per dipole level is very small for the energy, because there are so many of them, I end up creating enough intermolecular forces that I can turn gases into liquids and even into solids. Now, when I asked you to start ranking intermolecular forces, what you did was you put things into the bin for instantaneous dipoles if they were symmetrical. And so, for example, if I have helium or methane or propane or carbon tetrachloride, those 4 molecules right there are symmetrical, and therefore they go into the instantaneous dipole bucket. If I look at chloroform, it is an example of a molecule which has dipole-dipole interactions, and so you would expect it to have a higher set of intermolecular forces. And then you have molecules like methanol and water, which have hydrogen bonding sitting in them. So those would rank as having even higher intermolecular forces. And then you have sodium chloride and calcium oxide. These are ionic interactions. I don't include them here because the vapor pressures generated by salts are obviously negligible. So let's just hold on and look at these things which are liquids and gases right here. Now, this is how I want to do my ranking, and this must mean then that I can approximately say that as my intermolecular forces are going this way, they mirror the total amount of energy associated with sticking those molecules to each other. But remember, we're asking this in the context of vapor pressure. And we talked about how it was that there must be this sort of inverse relationship that existed, that as the intermolecular forces went up, the vapor pressure went down. And so, in fact, you see this inverse relationship right here. If I had to compare a helium to a water, obviously water, because it is so darn sticky, will have a very low vapor pressure. Whereas helium, because it has very little stickiness, will have a very high vapor pressure. And you see this all the time in class. I'll bring water in, I'll sit it down on a table, and you'll just sort of stare at it, and it's not seeming to do a whole lot. On the other hand, I pour some liquid nitrogen into a container. Well, it's got instantaneous dipoles. It's a very small molecule. There's very little intermolecular forces holding them together. They boil away incredibly quickly.